Hello, Nitish. Nitish.
Yes, sir. Yes, sir.
Yeah, is it audible now?
Sir, audible.
These slides in have I sent the slides to you?
No, sir.
Slides and notes of this module 1 I'll be sending you after this video, right? So video admele
Okay, sir.
nimige notes matte slides enidiyalla, like these slides are too much in depth ide. So
sir.
Students ಮಾಡಬೇಕಾದ್ರೆ like ಒಂಥರ too much according to the book information ಏನಿದೆ ಅದಕ್ಕಿಂತ in depth ಇದೆ. So for that like you can concentrate only on the figures and some set of equations. Okay, so ಯಾಕಂದ್ರೆ ಇದು ಯಾವುದು DC characteristics of inverter CMOS inverter ಏನಿದೆ, this involves a lot of equations. ಆದ್ದರಿಂದ ನಿಮಗೆ ಎಕ್ಸಾಮಿನೇಷನ್ ಪಾಯಿಂಟ್ ಆಫ್ ವ್ಯೂ ಯಾವ ಈಕ್ವೇಷನ್ಸ್ ಯಾವ ಸರ್ಕ್ಯೂಟ್ ಇಂಪಾರ್ಟೆಂಟ್ ಅಂತ ಹೇಳ್ತೀನಲ್ವಾ, ಸೊ ಬೇಸ್ಡ್ ಅಪಾನ್ ದಟ್ ಪ್ರಿಪೇರ್. ಓಕೆ
ಓಕೆ.
ಸೊ ಇಲ್ಲಿ 3 ಪಾರ್ಟಿಸಿಪೆಂಟ್ಸ್ ಆಡ್ ಆಗಿದ್ದಾರೆ, ನಿತೀಶ್ ಕುಮಾರ್ ಅಂಡ್ ಡಯಾನಾ. Like 2 more are absent, I think. So yeah, so regarding last class, this was the CMOS inverter circuit. So like in the slides, what you can see is, yeah, here it is. So the starting slide of a CMOS inverter, like we start with the logical circuit. So in circuit only one PMOS ide, one NMOS ide, and these are the various voltages. So for example, if I take this PMOS tondre, VGS comma P, VGS is the input voltage for this PMOS, okay, and VDS is the drain to source voltage of this PMOS. Similarly, VDS comma N andre even the NMOS ge drain to source voltage, VGS comma N andre even the NMOS ge gate to source voltage. And we know that the source of PMOS should be going for VDD and the source of NMOS should be going for ground. So here, based upon the magnitudes or the values of VDSN or VDSP or VGSN or VGSP, so these devices can be staying in 3 states. ಅಂದ್ರೆ ಒಂದು ಕಟ್ ಆಫ್ ಆಗಿರ್ಬೋದು, ಒಂದು ಸ್ಯಾಚುರೇಷನ್ ಆಗಿರ್ಬೋದು, ಇನ್ನೊಂದು ಅದು linear ಆಗಿರ್ಬೋದು. So these devices, like either NMOS or PMOS, can be staying in either cutoff region or saturation region or linear region based upon the magnitudes of these voltage values like VDSN or VDSP or VGSP or VGSN. So like here in the last class, we had discussed that this VGS comma P, andre even the PMOS ge VGS comma P is the input voltage across the gate and the source. So this should be equal to minus of VG minus VS, where VG is the input voltage and VS is the source voltage, and the source of this PMOS is going for VDD. So where VGS comma P is equal to minus of VDD minus VSN. So but the like so-called standard notation is I should be referring this VGS comma P as VSG, where VSG is VS minus VG, where VS, okay, so this VS for the PMOS is going for VDD and VG is going for VN. Hence, so this VGS comma P should be actually VDD minus VSN, and why we are taking it as minus of VDD minus VN is, like instead of VSG, here I am using VGS, okay. Hence for this reason, like this becomes minus of VDD minus VN. And regarding this VDS comma P as well, VDS comma P is here, okay, as mentioned in the circuit, where VDS comma P is minus of VDD minus V out, okay, where this VDS is VD minus VS, where VD is the drain voltage and that is going for V out, and VS is going for VDD. So here actually it should be VSD comma P. So but here we are referring it as VDS. Okay, hence it is minus of VDD minus V out. So here, based upon say these VGS comma P, VDS comma P, VGSN and VDS comma N. So here, based upon the voltage values, so these devices can be staying in three regions: active or saturation or cutoff region. And like I also told, so that so this NMOS and PMOS they will be in off region or in linear region based upon these equations. Say for example, this NMOS will be in the off condition when the input voltage applied to the NMOS gate is less than threshold voltage. Similarly, NMOS will be in the linear region if the VGS value or Vin value is greater than VTN and output voltage VDS is less than the effective voltage. This VGS minus VTN is called as the effective voltage. Similarly, you can remember the conditions for this PMOS to be in off condition and the condition for PMOS to be in the linear region. So here, based upon this, we have the application of various input voltage for my CMOS inverter starting from 0 voltage to say so 1 voltage, 1 volt, and here it is say 2.5 volts. Here it is. So like here the value of this Vin is applied as 2.5 volts, and here it is for 5 volt. So from 0 to 5 volt, the input voltage is been varying, and we analyze so whether my NMOS and PMOS will be in cutoff region or linear region or in saturation region. So only for the first condition where Vin is equal to 0, I will be analyzing these equations. Okay, same thing. You can see the equations for Vin equal to 1 volt and Vin equal to 2.5 volts and Vin equal to 5 volts. Okay, I repeat, only for the first case where the first case 1 is Vin equal to 0 volt, like we'll apply and we'll analyze the conditions of NMOS and PMOS devices by taking VTN is equal to 1 volt and VTP equals to minus 1 volt. So what are these VTN and VTP? VTN is the threshold voltage of NMOS. VTP is the threshold voltage for PMOS. Okay, so we have the threshold voltages for individual devices. Means, so we have the threshold voltage for this PMOS. We have the threshold voltage for NMOS. Okay, and we know that always the threshold voltage for this NMOS will be positive and threshold voltage for PMOS will be negative, as in here. See here. So this VTN is plus 1 volts and VTP is minus 1 volts. Right? Again, I'm repeating. Here we are analyzing just one condition where first condition is I'm applying Vin equal to 0 volts for this inverter. So here this Vin is applied with 0 volts. And according to the operation of inverter, at the output, what do you expect? If Vin is equal to 0 means V out should be equal to 1. So this condition is been analyzed by giving Vin is equal to 1. And we assume that VTN is 1 volts and VTP is minus 1 volts. So let's start. So by applying Vin is equal to 0 volts and assuming VTN equal to 1 volt and VTP equal to minus 1 volts, now we'll check the devices, how these devices will behave. Suppose if first see the NMOS operation. So for this NMOS, by looking at the circuit, VGS means input voltage for NMOS that is equal to Vin is 0 volts. Like as it is the case 1, and here this Vin is less than VTN. As this input voltage is 0 volts, means Vin is less than VTN. Hence, this NMOS will be in the cutoff region for Vin being 0 volts. And if you look at this PMOS, okay, so the input voltage for PMOS is VGS, P, and this VGS, P is given by minus of VDD minus Vin, where VDD is 5 volts and Vin is equal to 0. Hence, my PMOS is having its input voltage as minus 5 volts. Okay, and we know the threshold voltage of the PMOS as VTP is equal to minus 1 volts. And here we need to check the required condition. Suppose if this input voltage, so called VGS comma P, is less than VTP, where this VGS comma P is just now we have found out that it is minus 5 volts, is less than minus 1 volts as VTP. Suppose if it is the case, andaga, my PMOS will be in the on condition. So once device is in the on condition means it can be in either linear region or in the saturation region. ಈಗ ನಮಗೆ PMOS ಆಯಿತು ಅಥವಾ NMOS ಆಯಿತು, ಯಾವುದೇ ಒಂದು ಡಿವೈಸ್ ನಮಗೆ ಆನ್ ಆಗಿದೆ ಅಂದ್ರೆ, so that on device can be in two more state. One is the linear state as well as the saturation state. So once we have any device to be in on condition, we need to have one more check. So whether this on device is in the linear region or in the saturation region. So for that, what we do is we will check this parameter, driver voltage and VDS. So this VDR is the driver voltage, that is equal to VGS minus VT and VDS. ಅಂದ್ರೆ ನಮಗೆ ಯಾವುದೋ ಒಂದು ಡಿವೈಸ್ ಆನ್ ಆಗಿದ್ರೆ ನಾವು ಅದನ್ನ ಆನ್ ಅಂದ್ರೆ ಏನರ್ಥ, its on condition indicates that the device can be in linear region or in the saturation region. ಅಂದ್ರೆ ಆನ್ ಡಿವೈಸ್ ಯಾವ ರೀಜನ್ ಅಲ್ಲಿ ಇದೆ ಅನ್ನೋದು ಚೆಕ್ ಮಾಡಲಿಕ್ಕೆ we have one more check. That means we will check this driver voltage, so called VGS minus VT, and VDS value. See how it is done. So first let us check this VDS comma P. So where VD is VDD and source voltage is V out, right? Hence I'll be getting this as minus 5 equal to 0 volts. Second is I'll check VGS comma P minus VTP, where VGS comma P is minus 5 and VTP is minus 1. Minus into minus is equal to plus agata, hence it is plus 1, and we get the answer as minus 4. Now we'll have a check. Suppose if this VDS comma P is greater than VGS minus VT, then my device will be in the linear region. Okay, so this step means this particular case 1 for V equal to 0 volts. Okay, now we'll check the status of NMOS and PMOS. Suppose if any one device is in the on condition, again we'll have a check whether my PMOS or NMOS is in linear region or in saturation region by having this equation, by having the calculation of VDS comma P and VGS minus VT. Suppose if this VDS comma P is greater than VGS minus VTP, andaga my device is in linear region. Okay, so this same step is been repeated for case 2, where case 2 is we will increase Vin to 1 volt, right? Like earlier the case 1 was Vin was kept equal to 0 volts. Now case 2 is I'll increase Vin to 1 volt. Okay, and like of course V out will be equal to 5 volts. Like again we'll check the conditions of NMOS here, and so next the driver voltage of NMOS. So next we'll check for the PMOS. Okay, so here same condition is applied. I mean same steps have been applied here for the third case as well, where the third case, as you can see here, so this third case, case 3 case 3 is Vin is equal to 2.5 volts. Okay, and fourth case is Vin is greater than or equal to 4 volts, and case 5 is Vin equal to 5 volts. Okay, so by having all the checking of all the devices in various regions and the respective voltage values, we will have this particular table. Okay, so for case 1 we had V is equal to 0 and V out is equal to 5 volts, and we saw that NMOS was in cutoff region and PMOS was in linear region. In the slides I have just discussed the first condition, and I told you people to analyze the remaining 4 conditions. Okay, same steps are there like what we have discussed in the first condition, and we saw that NMOS was in cutoff region and PMOS was in a linear region. Okay, same thing can be seen here also. When this Vin along the x-axis is equal to 0 andaga, what is the value of V out? V out is equal to 5 volts. See, here it is. Like so this V out is high. When Vin is equal to 0, the output voltage is high. Okay, so for all the values between 0 and Vin, the output is output V naught is high. Similarly, if I have V in as greater than or equal to 1 volt, like in that case also V naught is less than 5 volt, like somewhat decrease we have in the output voltage. And like in region 3, like somewhere here in the third point where V in is equal to V out is equal to 2.5 volts, what we have is both my devices NMOS as well as PMOS will be in saturation region, means both will be in the on condition. Hence we have V in is equal to V out is equal to 2.5 volts, and this 2.5 volts is half the value of VDD, means this point it is. Okay, so this point is coinciding with the third point here, as you can see the mouse. Okay, again in the fourth region, means fourth region is this one. Okay, like here the conditions of my device will be my NMOS will be in the linear region and PMOS will be in the saturation region. Again here this is the region 5. Okay, the region 5 here the NMOS will be in linear region and PMOS will be in the cutoff region. Okay, so from examination point of view, like this table is very much important, as well as to indicate 1, 2, 3, 4, 5 regions in the DC curves of the CMOS inverter is very much important, as well as the scales here. Like this is the origin and this is V in and this point is VDD by 2 and this point is VDD plus VTP and this is the VDD like equals to 5 volts. Okay, so here this input voltage is varying between 0 to 5 volts. Okay, according to here, the case 1, case 2, case 3, case 4, case 5, where V is equal to 5 volts, and here V is equal to 0 means it is here, and V is equal to VDD is equal to 5 volts is here, and that is shown in the table as case 5, where V is equal to 5 volts. Okay, so by varying the input voltage from 0 to 5 volts, how we have the output voltage and the behavior of my NMOS and PMOS device is being indicated here. And in the graph, you can find here 5 regions. Okay, the region 1, region 2, region 3 is here, region 4 is this one, and region 5 is this one. So from examination point of view, you can simply write down this first case 1. See this case 1 clearly. Okay, and you can directly come to the last table. Okay, this last table along with this DC characteristic curves. Okay, yeah, like again we have the similar inverter here. Okay, same figure it is, and we have the symbol of this as well. Okay, and this is a CMOS inverter. Okay, CMOS inverter, like having PMOS and NMOS, same device like what we saw earlier. And like this is the truth table, where if V is equal to 0 means V out will be equal to 1, like opposite to 0. And if V is equal to high, andre output will be equal to 0. Okay, and like this figure is indicating that, okay, like in case of this PMOS device, right? In case, I mean like in place of this pull-up device, so-called PMOS device, I can have other alternatives. Andre even the PMOS ಜಾಗದಲ್ಲಿ ನಾನು ಬೇರೆ ಡಿವೈಸ್ ನ ಕೂಡ ಯೂಸ್ ಮಾಡಬಹುದು. ಆ ಡಿವೈಸ್ ಯಾವುದಾದ್ರು I can go for this passive resistor as the pull-up device, or I can go for MOS devices, namely NMOS depletion type device ಕೂಡ ನಾನು ಈ PMOS ಜಾಗದಲ್ಲಿ ಯೂಸ್ ಮಾಡಬಹುದು, or I can go for NMOS enhancement type device ಕೂಡ ಯೂಸ್ ಮಾಡಬಹುದು, right? Hence, like this empty box is showing it as pull-up device. PUD means pull-up device. Given the pull-up device ನಾವು ಯೂಸ್ ಮಾಡಿದೀವಿ, PMOS ಯೂಸ್ ಮಾಡಿದೀವಿ. ಅದೇ ರೀತಿ ನಾನು ಈ PMOS device as a pull-up device ಜಾಗದಲ್ಲಿ ನಾನು like I can go for a use of this passive resistor, or I can go for NMOS depletion type device, or I can go for NMOS enhancement type device ಕೂಡ ನಾನು ಈ PMOS ಜಾಗದಲ್ಲಿ ಅಂದ್ರೆ ಈ pull-up device ಜಾಗದಲ್ಲಿ ಯೂಸ್ ಮಾಡಬಹುದು. And by default you have this output capacitance. ಅಂದ್ರೆ ಇಲ್ಲಿ ಈ ಜಾಗದಲ್ಲಿ ನಮಗೆ by default ಒಂದು output capacitance ಕೂಡ ಇರುತ್ತೆ. Okay, of course, like that will be not shown in all circuits. So by default you have this output capacitance for this inverter at the output point here. Okay, right. So what we saw, this particular curve is the practical curve. Okay, upon the variation of input voltage from 0 to 5 volts, you have the behavior of the devices of inverter, namely this NMOS and PMOS will be behaving like this, means operating in the various regions. So, but this curve is the ideal curve, right? Like ideally, the inverter should be having the DC characteristic curve like this. Okay, like this indicates what? If V is equal to 0 iddaga, what about output? Output will be equal to VDD, or input 0 iddaga output to 5 volts irutte. Adhe reeti input illi input 5 volts iddaga output enagide 0 ide, right? So here if V is lying between 0 to VDD by 2 andre VDD of 5 volts ತಗೊಂಡ್ರೆ 5 divided by 2 equals to 2.5 volts. So ನಮ್ಮ ಇನ್ಪುಟ್ ವೋಲ್ಟೇಜ್ ಇಲ್ಲಿ 0 ಮತ್ತು 2.5 volts ಇದ್ದಾಗ ಔಟ್ಪುಟ್ ಏನಾಗಿದೆ? Output is equal to 1, means if this beam is lying between 0 to 2.5 volts or VDD by 2 ಇದ್ದಾಗ ಔಟ್ಪುಟ್ ಏನಾಗಿದೆ? ಹೈ ಆಗಿದೆ. ಅದೇ ರೀತಿ say from VDD by 2 to VDD ಔಟ್ಪುಟ್ ಏನಾಗಿದೆ? 0 ಆಗಿದೆ. Here it is. ಅಂದ್ರೆ ಇಲ್ಲಿಂದ ಈ ಪಾಯಿಂಟ್ ತನಕ ಔಟ್ಪುಟ್ ಏನಾಗಿದೆ? 0 ಆಗಿದೆ. ಸೊ ಹಿಯರ್ ಇನ್ಪುಟ್ ಇಸ್ ಅಬ್ರಪ್ಟ್ಲಿ ಚೇಂಜಿಂಗ್ ಇನ್ ದ ಮಿಡಲ್. ಅಂದ್ರೆ ಈ VDD by 2 ನಮಗೆ ಏನಾಗಿದೆ? ಈ ಪಾಯಿಂಟ್ ಅಲ್ಲಿ ಏನಾಗಿದೆ? The input is abruptly changing in the middle at VDD by 2, and this point we call it as the threshold voltage of the inverter. Like I said, we have the threshold voltage for PMOS. We have the threshold voltage for NMOS, means individual device kuda namage threshold voltage irutte. Adhe reeti for this whole inverter also you have a separate threshold voltage, and that we call it as VT, where VT is the inverter threshold voltage for this whole inverter. Okay, so this usually, so this inversion is occurring when input Vin is equal to V out. That is when Vin is ಏನಾಗಿದೆ ನೋಡಿ, ಈ ಪಾಯಿಂಟ್ ಅಲ್ಲಿ Vin is VDD by 2. ಅದೇ ರೀತಿ Vin is ಈ ಪಾಯಿಂಟ್ ಅಲ್ಲಿ ನಮಗೆ ಈ ಪಾಯಿಂಟ್ ಅಲ್ಲಿ Vin is equal to VDD by 2 and output is also VDD by 2, means Vin is equal to V out, where Vin is VDD by 2 and V out is also VDD by 2. Okay, so we don't have the through path from VDD to ground, means only one device will be active at any instant of time. Say for example, even the input 0 ಆಗಿದ್ರೆ PMOS ಆನ್ ಆಗುತ್ತೆ, NMOS ಆಫ್ ಆಗಿರುತ್ತೆ. ಅದೇ ರೀತಿ Vin ಹೈ ಇದ್ರೆ NMOS ಆನ್ ಆಗಿರುತ್ತೆ, PMOS ಆಫ್ ಆಗಿರುತ್ತೆ. This means that at any instant of time, you don't have a direct path between high potential to the low potential. Means ನಮಗೆ ಯಾವುದೇ ಇನ್ಸ್ಟೆಂಟ್ ಅಲ್ಲಿ ನಮಗೆ ಎರಡು ಡಿವೈಸ್ ಆನ್ ಆಗಿರೋದಿಲ್ಲ. Okay, means any one device will be on at any instant of time. Hence, we don't have a direct or through path between high potential to low potential. Means the current will not be having a direct path from VDD via PMOS via NMOS to the ground. Okay, yeah. So this is the table given according to the book. Okay, here also we are having the same basic circuit ಏನಿದೆ. So first slide ಅಲ್ಲಿ CMOS inverter having VGSN, VGSP, VDSN, VDSP ಏನು ವೋಲ್ಟೇಜ್ ತೋರಿಸಿತ್ತು. ಓಕೆ, ಆ ಒಂದು ಸರ್ಕ್ಯೂಟಿಗೆ here is the relationship between voltages for the three regions of operation of a CMOS inverter. Those are namely cutoff region, linear region, and saturated region. So this table relates output voltage to input voltage, where VTP and VTN are considered, and this VTN is positive and VTP is always negative. As the source of NMOS is grounded, hence VGSN is equal to Vin and VDSN is equal to V output. So you can see these equations in the circuit. Okay, so you can clearly see that. So as the source of PMOS is tied to VDD, okay, VGSP is equal to So this VG minus VS, where VG is Vin and VS is VDD, and VDSP is VD minus VS, where VD is Vout and VS is VDD. So here we consider that IDSN is equal to IDSP, where IDSN is the ID current of NMOS device and IDSP is the IDSP is the drain current in the PMOS device. So like if I see this particular table, like here, so for NMOS device, my NMOS device will be in the cutoff region if this input voltage or VGSN for my NMOS is less than the threshold voltage of NMOS device. Okay, so this VGSN is nothing but input voltage. Okay, so this VGSN is nothing but the input voltage for the NMOS, means V in it is. Okay, similarly, my NMOS will be in the linear region when the input voltage or VGSN is greater than VTN or Vin is greater than VTN. Again, we have one more condition that VDSN or the output voltage of NMOS device must be less than the effective voltage, or this VDSN means what? It is Vout for NMOS device. So this Vout should be less than Vin minus VTN. So if my NMOS is satisfying all these equations with respect to this VGSN and VTN, and Vout is less than V minus VTN, then my NMOS will be in the linear region. Okay. Likewise, we have this condition for my NMOS to be in saturation region, where of course VGSN is greater than VTN. Okay. So, but regarding this VDSN, okay, like earlier, if this VDSN is less than the effective voltage, then my NMOS will be cut off. I mean, supposing this VDSN is less than effective voltage, then my NMOS will be in linear region. VDSN is greater than the effective voltage, then my NMOS will be in the saturated region, right? Similarly, for this PMOS also, you can remember this equation as well as, so for linear region, this equation, and for saturation region, where Vout is less than V minus VTP. Okay, so these equations are coming from, right? I repeat, these equations are neatly discussed along with the numerical examples in 5 cases. So the case 5 is, so for example, this case 5, where we have taken V is equal to 5 volts and Vout is equal to, of course, 0. Why? Because input high, then output lower. And we'll be analyzing the conditions of NMOS as well as for PMOS. Similarly, the case 4 was V in is greater than or equal to 4 volts. Okay, so the output, what we can achieve from these calculations is this whole table. From examination point of view, so you can write down this particular table, or you can take the help of this table also. Okay, so here, like the conditions of the regions, say this NMOS cutoff and PMOS linear and NMOS saturation and PMOS linear is expressed. So these regions are expressed in terms of equation, nothing more than that. Okay, right. But again, same thing is being given here. So where VGSP is nothing but VG minus VS, where VG is Vin and VS is VDD. Like same equations are being expressed like in a single slide. So for easy reference. Okay. So where Vin is VGSN for NMOS and Vout is VDSN for NMOS device, and VGSP is negative always for PMOS device, where this VG is Vin and VS is VDD. And if I take VDSP and daga, so for the PMOS device, VDS is the output voltage minus VDD. Same thing has been expressed in a single slide. And here are the graphs, like this is for the NMOS device and this is for the PMOS device. Like how to identify that? Like here we have this VDSN and IDSN, and like this is for NMOS device, and this quadrant, third quadrant, is for the PMOS device, where along the X, like we have taken minus VDSP, and here it is minus IDSP. Okay, and if you like, so just overlap these curves, means I'll be having this particular graph. Okay, again, like it is showing the same thing, means what? Here it is. Okay, like in the region 1 where Vin is equal to 0, my NMOS will be in the cutoff region. And if Vin is equal to 5 volts, means my PMOS will be in the cutoff region. Okay, so these conditions are just overlapped, right? Like in the graphical manner, like so as to achieve this particular graph. Okay. So again, same thing is been given here. Same curve, same DC characteristic curve, like having 5 regions: A region, B region, C region, D region, and E region. Okay, same thing, like how the device will be, behaving in like how device will be behaving in the linear region, cutoff region. Okay, same equations. Yeah, right. So let me stop right here. Like in the next class, like I'll be dealing with something called as a skew rate. So we have the equivalent circuit of the CMOS inverter, like in region A and region B, like and C and D, like how the circuits are being formed. So based upon the region of operation of NMOS and PMOS, okay, and as well as the something called as beta ratio effects. Okay, so right now we can log out, and say from today's class you can practice the equations or the worst case like this particular table, or else you can have the practicing of this particular table in short, right, along with the first condition what we had discussed when B is equal to 0 and my NMOS was able to operate in the cutoff region and PMOS was in the linear region. And do practice this figure. Okay, so same curve it is, like having A, B, C, D, E regions. Okay, right? So you can like do practice these equation and these graphs. And in next class, like I'll be dealing with the circuit construction for each and every region of operation. Okay, along with the beta ratio effects. Okay, so you can log out now. Okay, thank you.